In this section of chapter 2.2, we explore the transpose of a matrix. So the transpose is written the matrix symbol with a T up in the exponent. So for matrix A, we would write the transpose as A with a T up in the exponent place symbolically. We're not actually doing any exponent calculations. So the transpose A T of a matrix A is formed by writing its columns as its rows. So notice here the values that are in the bottom part of the triangle of the matrix, so A21, A31, all the way through AM1, are replaced over here in the upper triangular part of the matrix. So if you have a square matrix, your matrix stays the same dimensions, but if your matrix is not square, then the dimensions flip. So notice A is a M by N matrix, and A transpose is a N by M matrix. If you can see, here's the N rows and M columns. All right, so we are going to find the transpose of A here. So we can say A transpose is going to be 931 in the top row, because I'm taking these column values and translating them to rows. 305 in the next row. And then -7, -8, 2 in the next row. And 0, -4, and -8 here in the last row. So A was a 3x4 matrix, and A transpose is now a 4x3 matrix. So here are the properties of the transpose. So if you transpose the transpose, you just get the matrix itself back out. The second property is that if you add matrices and take the transpose, that's the same as if you transpose each matrix and then add them up. The third property is scalar multiplication. So if you multiply the matrix by a scalar and then take a transpose, that's the same result as if you transpose the matrix and then multiply through by the scalar. So that C here is a scalar, we call it a constant. And then the fourth property is the transpose of a product is the second value or the second matrix in the product transpose multiplied by the first matrix transpose. So let's head into Sympy and verify some of these properties. All right, I'm going to enter matrix A. So A is going to be the matrix we were working with. So the rows are 9, 3, -7, 0 for the top row, and then 3, 0, -8, -4 for the second row, followed by 1, 5, 2, and -8 in the third row, and then we can just verify, type A, and we should get out the exact match for the example we were just looking at. And then I'm gonna, so A is a 3x4 matrix. I'm gonna make up another matrix B that is also a 3x4 matrix so that I can add it with matrix A. Remember, if you're adding matrices, they need to have the same dimensions. So B is going to be 1, 2, 1, 2 in the top row. And the second row of B will be, let's see, 2, 1, 2, 1. And for the third row of B, we can call it 3, 4, 3, 4. And we can type B just to verify matrix B here. All right. Okay, so to verify property 1, we want to define the transpose of A. So there's two ways you can do that in Sympy. One is to say transpose, if I spelled it right, of A in here. and we get the transpose, which is an exact match for what we calculated by hand. The other option is to say A dot T, and that also gives us the same result. So I'm going to call it matrix D is going to be equal to A dot T. And then I'm going to do D transpose. So I'm going to type D dot T, and I should get back out matrix A. Voila, it's a match. So we see the transpose of the transpose just brings us back to the original matrix, and that makes sense because we're just flipping columns and rows, and then flipping them back should return us to the original matrix. Okay, our second property involves addition. So I'm going to have to define a new matrix. I'm going to call it E equals A plus B. And then here's E, and you can double check the values, A and B, so they sum up each entry. And then I'm going to calculate E transpose, so E dot T. And here it is. So A plus B was a 3x4 matrix, and then the transpose of that is a 4x3 matrix. All right, I've already defined A transpose, that's matrix D. So I need to define a matrix that's going to be B transpose. So I'm going to call that G. A lot of letters here to keep track of. And we can verify, here's matrix G. It is a 4x3 matrix, and it's just a transpose of what matrix B was. So now I'm going to add matrix D and G, and then I need to transpose them. So I'm going to come up with a new letter for D plus G because I'm trying to prove, oh no, I just have to add D and G because I already added A and B. So A and B added was E, and there's E transpose. So if I do D plus G, that's going to be A transpose plus B transpose, and it's a match for the sum transpose, which is E transpose. All right, so we've just shown property 2. Property 3 is scalar multiplication. So I am going to define matrix C as 4 times A. So that just took all the entries of A and multiplied them by 4. And then I want to see what C transpose is. So this is the left side of property 3, the scalar multiple transposed. And now I'm going to do 4 times A transpose, and A transpose was what we call D. So 4 times D also gives me the same results. So we verified here matrix property 3. Great. All right, so the last matrix property we want to verify is property 4, which says that the product transpose is equal to the second part of the product transpose multiplied by the first part of the product transpose. All right, so I'm going to define a product matrix that'll be F, and that's going to be A times B. Oh, and I ran into an error here. And we can't multiply A times B because they're different dimensions. Okay, so I need a 4x3 matrix. So conveniently, I have B transpose, which we call G. So A times G should be able to multiply. We'll call that F. All right, so let's look at F. So F's multiplication gave us a 3x3 matrix. And then if we do F transpose, F dot T, there's a transpose of that. So that should be the same thing as if we do G transpose times A transpose. So let's check and see if I do G dot T times A dot T, if it'll give me the same results. And it liked it. Voila, we've got a match here. So you can verify these properties of the transposes. A good way to do it is just by working through examples. And then we're going to go talk about symmetric matrices. Okay, before we talk about symmetric matrices, let's talk a little bit more about property 4 and why the order changes when we multiply. So we were multiplying matrices A and G. So A was a 3x4 matrix, and G was B transpose, and we did that to get a 4x3 matrix. So A times G is a 3x3 matrix. Because we're taking the rows of A and the columns of G for the dimensions of our matrix product. Then A times G transpose is also a 3x3 matrix. All right, so let's think about the second side of this. If we are calculating A transpose times G transpose, if we just went in the normal order, well, A transpose is a 4x3 matrix, and G transpose is a 3x4 matrix. So their product, A transpose times G transpose, is going to be a 4x4 matrix. So that's not the right dimension match that we're going for, right? If we've got A times G, and then we're transposing that, that should also be a 3x3 matrix. So you can see just from the dimension analysis that dimensions-wise, to get all the pieces in the right spot to multiply to end up with a matrix that's equivalent to A times B, then transposed, you have to have the second matrix transpose multiplied by the first matrix transpose, because G transpose times A transpose will be a 3x4 matrix times a 4x3 matrix. So G transpose times A transpose is the 3x3 matrix that we're looking for. And you can, write them out by hand and see how the actual values move and rotate through this process. So we see this 3x3 matrix ends up with the products in the right places that we're looking for. All right, so we say a matrix is symmetric if and only if its transpose equals itself. So this is a symmetric matrix right here, matrix M. Notice the values in the lower triangle are an exact reflection of the values in the upper triangle. So that's how we identify, just quickly visually, a symmetric matrix. And so we want to prove that the product A times A transpose gives you a symmetric matrix for any matrix A. So let's look at this. Okay, so we've got A times A transpose, and we want to show it's symmetric. So it's going to be symmetric if its transpose equals itself. So let's take the transpose of that and see what we get. All right, by our matrix properties, if we head back to the properties, by property 4, we can distribute that transpose through and reverse the order of multiplication. So this is going to be a transpose, because that was my second matrix here in the multiplication, multiplied by A transpose. So that is going to be by our first matrix property, A transpose just gives us back out A. And then the second matrix is A transpose. So we just showed if we take A times A transpose and transpose it, we get back out the same result. So anytime you're trying to build a symmetric matrix, just take matrix A, multiply it by its transpose, and there's a symmetric matrix. All right, in the next section, we're going to learn about the inverse of the matrix. So this concludes section 2.2's videos, and then we'll look at the inverse in section 2.3.